Everybody, welcome. In Taiwan, it's 4 o'clock in the afternoon, and I think in Africa, it must be morning. Welcome to the talk by Dr. John Habarulema of the South African National Space Agency. SANSA is the name. In Hamanus, yeah. And John said that it's not far from Cape Town, only 120 kilometers. John received the 2016 AGU Africa Award for the research excellence in space science. So I think it's a very important recognition for him and also for the African space scientists. And John did his undergraduate in Uganda and his PhD from Rhodes University in South Africa, 2011. And he has been working on the total electron content measurements since then. And I think that he is now an expert in this area. And we are very happy now to have him here because if we are talking in terms of lower latitude ionospheric physics research in the context of global scale, and obviously Africa is a very important. I would say, I might even say it's a missing link. So we welcome him, to the club, so to say. And John, can you start your talk now? It's all yours.
So I was presenting to myself. So what I was saying was that there is a link between atmospheric draft waves and TIDs. And we know that commonly these draft waves are generated in most cases in the troposphere by mainly wave fronts or airflow over mountains. And in the graph which you are seeing, I'm showing wind speed as a function of height. And these small wiggles that one sees between 80 up to about 120 kilometers. So that's partly within the D region and E region. Those are indications of atmospheric draft waves. And so one can see them in wind speed, in temperature, and very many other atmospheric parameters. Now, we know that the amplitude of these draft waves do increase as they reach high heights, and that is because you are propagating within the thin air, and that leads to breakup. And when you have that kind of breakup, then you transfer energy and momentum from the troposphere to the stratosphere of the mesosphere. But in this talk, we are concerned with these TIDs within the ionosphere. And so, of course, within different layers themselves, these draft waves are going to transfer this energy and momentum between different regions as they propagate. And for historical perspective, we know that these TIDs were discovered a long time ago in 1948, and up to now, it's still an active area of research simply because they have practical applications, but there are also some theoretical understanding that we still do not understand. Okay, so let's try to look at how these kind of waves interact when they propagate within the ionosphere. And for this, we are starting with the continuity equation, which is equation 1. And in that equation 1, you can see QE and LE. So QE is the production rate and LE is the loss rate. And NE there is the electron density, while VE is the velocity of the electrons. Now, if we assume that we have initially a background or stationary condition, then if we have a gravity wave which is passing, then we can split the background electron density. We can split the electron density into the background and the perturbed component as a result of the passage of this gravity wave. And that's what we are having here as NE, which is equal to NEO. So this NEO will be the background plus the perturbed component. Now we can also assume that the velocity which is induced by the gravity wave is VE1, and therefore the velocity itself will also be written as a function of background velocity and the perturbed component. Now we can go further and assume that the production rate and the loss rate are negligible, and we set the initial velocity to 0, and therefore we come up with the electron density perturbation term NE written as a function of the background electron density and the perturbed velocity component, which is equation 2. Now, that equation 2 can be written later as equation 3 if we introduce in the velocity of the neutral gas and the effect of Lorentz force and ion drag. And so this one will be the effect of the Lorentz force, and the rest will be the ion drag. And in this equation, ME is the mass of electron, VE is the collisional frequency between the electrons and the neutral gas, and Vn here will be the neutral gas velocity. And B, of course, is the Earth magnetic field. Now, the solution to the equation number 3 will be this equation number 4. And of course, we will not go into details, but the important things which I'm going to point out, of course, will be this perturbed component, VE1, and the omega CE, which is the electron cyclotron frequency. And B, in this case, is our unit vector in the direction of the geomagnetic field. Now, let's make an assumption that we are working within the F region, and as we know, the collision frequency within the F region can be negligible, and therefore our VE1 in equation 4 is going to reduce to equation 5. And therefore, the response of the electron density perturbation as a result of the gravity wave propagating through the ionosphere can be written as equation 6. Now, we can make further assumptions, which I want to go into, and then that will lead into equation 7. And the important thing which I want to point out in equation 7 is that the perturbed electron density is a function of the background electron density. And so when we are doing gravity wave studies or TIDs, we've got to be able to estimate the background electron density. And I think that's the most important message that I wanted to point out in equation 7. Now, if we look at studies of a long time ago, the first figure, I took it from a paper of Pinga in 1979, and they are using the radar measurements, different range gates, and this kind of appearance of peaks in different observations as a function of time is a manifestation of an atmospheric gravity wave or a TID. And it's looking in different directions at 30 degrees and 60 degrees, I think, towards the southern hemisphere. Now, in the bottom part, the left-hand side, I'm showing a theoretical simulation from the coupled thermosphere, ionosphere, plasma sphere model. These are simulations at a fixed pressure surface at an approximate altitude of 380 kilometers. And you'll see that on the left, we have the negative values, and on the right, there are positive values in terms of latitudes. And so it's from the southern hemisphere to the northern hemisphere and vice versa. And on the left, we have the fractional change in height. And on your right, we have time. And what this graph is essentially saying is that when you have these gravity waves which result into TIDs in the ionosphere, you can have these ones propagating from either southern hemisphere or northern hemisphere to the other hemisphere. And therefore, these are what are called equatorial propagating gravity waves. Now, on your right, we are showing the CHAMP relative density variations during the storm of the 7th to 8th November 2004. And these are only night side observations. And on your x-axis is time in terms of days, and on the y-axis is the geographic latitude. And once again, you can see the indications of these waves which are propagating from either northern hemisphere to the southern hemisphere or vice versa. So this is just put into perspective that you can have this kind of gravity waves propagating from either hemisphere and crossing over to the other hemisphere. Now, in terms of categorization, we know that the main categories are medium-scale TIDs and large-scale TIDs. And depending sometimes on conditions, they have different source mechanisms. Medium-scale TIDs, in most cases, travel in all directions, depending on the prevailing conditions. And the sources include auroral regions, tropospheric systems, sometimes solar terminators, eclipses, and very many other mechanisms. Large-scale TIDs, in most cases, propagate equatorward from auroral regions, and these are mainly observed during geomagnetic storms. And so the main mechanisms are Joule heating, Lorentz coupling, and particle precipitation. Now, if you look at your left-hand side, you'll see the observations of TIDs, and these are medium-scale TIDs at different times, represented in a polar plot. And as I was saying, they can propagate in any direction, as this plot shows that I took from the paper of Hernandez Pajeres in 2012. On your right-hand side, you see these black arrows. Of course, on the x-axis, we have time. On the y-axis, we have latitude. And so you can see these observations over southern Africa. And the arrows are showing the propagation of these kind of waves from southern hemisphere towards the geomagnetic geographic equator. And we know that medium-scale TIDs have periods of up to an hour. Velocity values usually between 100 to 300 meters per second, and we know that they occur more frequently. On the other hand, large-scale TIDs have velocities up to 1,000 meters per second, and sometimes during storm conditions, they can exceed this particular value. And the periods are usually between 1 to 3 hours. Now, but the focus of this talk today is to look at the results or the observations of TIDs, and both categories will be discussed during storm conditions, but with the main special emphasis that the ones which I'm going to talk about in the coming slides will be the ones which are coming from low latitudes. And the other important aspect that we talk about is what is launching those waves from low latitudes. So this is a typical example of what I'm going to show. And this is over the African region, as you can see. On the x-axis is time, on the y-axis is geographic latitude. And this thick line, horizontal black line, is the approximate of the geomagnetic equator. You'll see that from around 40 degrees south, there are some arrows, black arrows, which are pointing from south to north. Those are the equatorward propagating waves, or TIDs. And then from the equator, what you can see, these arrows where one is like a mirror of the other, are what we are calling the forward TIDs, and forward in both hemispheres, which means that they are coming from the geomagnetic equator. And these are the results which I'm going to show on a statistical scale. And of course, the Wakara bar is showing changes in TEC, which I'll explain later how we derive that. Okay, so one of the important things, of course, when you're studying this kind of TIDs or any kind of TIDs, is that you've got to be able to estimate the background. There are different methods of estimating background, and some people will use running averages, others will use some kind of mean for some specific number of days preceding the storm. And in this study, we are using a simple method of polynomial fits. And so we are fitting a polynomial of, I think it's a fourth order polynomial. And once you do that on a global scale, for example, on your left-hand side, you'll see that the TEC themselves are plotted in the blue color, and the fitted values are in red. And this is for one PRN, period number 3, over a station in Addis, which is in the equatorial region. And the other PRN4 is in South Africa, which is in mid-latitude. And when you subtract the fitted values from the actual VTC values, you get the delta TEC, which is what we call TEC perturbations. And obviously, you can say the perturbations in equatorial latitudes are greater in terms of magnitude than the perturbations in mid-latitudes. And once you do that on a global scale, you get this kind of movie that is playing for the 9th of March 2012. Now, this movie is very busy if you look at it, but I will perhaps request you to focus on the dotted line, which is the geomagnetic equator. And you'll see, so let's look at this one, which is coming now over the South American region. You'll start seeing some enhanced values which are building up around the geomagnetic equator. And you can see they are moving downwards. And on the northern hemisphere as well, they'll be moving also towards the mid-latitude, the other side. And that is what we call the TIDs, which are originating from the geomagnetic equator. And in this case, we call them forward TIDs. Okay, so what have we done on a statistical basis to try and quantify how often we see this and what is the driving mechanism? What we did was to look at TEC changes during storm conditions, which occurred from 2010 up to 2018. And we are looking at two longitudinal sectors. So we look between 20 to 40 degrees east, and that is the African sector. And then we look between 50 to 70 degrees west, which is the American sector. And these times, these longitude sectors are chosen in a careful way to make sure that the longitude sector of 20 degrees ensures that we don't have significant local time changes. The storm criterion we are using KP greater than 4 or magnitude of DST, which is greater than 50 nanotesla's. And the background TC estimation, we are using pronomial fitting. And once we've done that, we bin our TEC in 5 minutes by 0.5 degree grids. And then from that, we estimate our propagation characteristics such as velocity, periods, wavelength, and the rest. And for those who may be interested in this kind of estimation, especially the propagation characteristics, which I won't go into, you can look for the paper which has recently been published in JGR, and the details are right there. Okay, so let's look at a typical example. So this is over the American region, American sector, and the red lines are showing the region which we have covered. So that is between 50 to 70 degrees west. This is 20 degrees longitude sector. And then the rest of the examples. So let's focus on, for example, B. In panel B here, this is the latitude on your y-axis, and on your x-axis is time in UT. And this is delta TEC, which we've derived by subtracting the fitted values from actual TEC values. And in South America, this one, the dotted red line is indicating the approximate of the geomagnetic equator. And what we think are indications of this kind of waves which are coming from the geomagnetic equator is what is shown here. So the dots are fits. And you'll see that there is a line in the northern hemisphere above the equator, and there's another line in the southern hemisphere below the geomagnetic equator. You'll see they seem to be having a source origin from the same part, which is around the geomagnetic equator. And essentially part C, the graph in C and the graph in D are showing exactly the same thing, but for different storm days. And so you'll see that this seems to always be coming just above, sort of in the afternoons if we convert from the UT to local time. But we'll go to that later. We show a similar example over the African sector. Again, the African region is the one between the longitudinal sector we've covered is between 20 to 40 degrees east. And we'll look at part B again. And what we are showing is this one. So in essence, it does not matter whether you are looking at enhancements or whether you're looking at depletions. For the case of the African sector, for example, look at 10 degrees north. That's approximate of the geomagnetic equator. And you can see the fitted lines and the fitted line in the southern hemisphere, even if you follow the depletion, it is the same thing. And so the behavior in the northern hemisphere and the behavior in the southern hemisphere seem to be the mirror part of the other. And that's what convinces us that these kind of waves are having the same source origin, which is the geomagnetic equator. So let's look at the results over the American region. Now, we are looking again for results from 2010 up to 2018. So the first panel is the velocity values of these forward TIDs during the main and recovery phases. And the main phase is plotted at the blue dots. And the velocity of these waves in the recovery phase is plotted as the black crosses. You'll see that there are not many cases over the American sector between 2012 up to around 2014. And then we have some kind of, although there are not many, but the number increases from 2016 up to about 2018. Now, in part B, in the plot in B, what we have done is combine all the results for the main phase. And in this case, the velocity is plotted as the blue dots, and the period in hours is plotted as open circles. And of course, this period tells us whether we are looking at medium scale or large scale. And then we do the same for the recovery phase. And in the recovery phase, you can see we have two cases of this kind of waves which seem to be appearing during nighttime, but otherwise, most of the cases appear during local daytime. We know that UT, the local time is about UT -5 in South America. So let's look at a similar case of the African region. In the African region, once again, the velocity is on the y-axis, and on the x-axis is the time as in terms of years. And the main phase, again, is plotted in blue dots in the first graph, and the velocity of these waves in the recovery phase is plotted as black crosses. Now, clearly, we will see that there are more cases in the African sector compared to the American sector. And once again, let's aggregate everything and plot the main phase results and the recovery phase results differently. And these dotted lines themselves are showing the local time. So I think it's from 7 to about 18 local time. And the period, which is what is in the open circles, it's on your right-hand side of each plot in B and C respectively. You'll see that most of them have periods between 30 minutes and above. In terms of local time occurrence, we'll see that these kind of cases, both in the main phase and the recovery phase, predominantly occur during local daytime. Okay, so let's look at some of our results, and we'll have to remind ourselves about these kind of categorizations. Now we see that over the African sector, almost all observed forward TIDs during main phase are within the large scale category, and the velocities are between 300 and 550 meters per second. Now, during the recovery phase, a big chunk of that accounts for medium scale TIDs, and only 37% of that we've observed are large scale. Now, statistically, the results of the American sector are not really different from the results over the African sector. And the main conclusion from all of them is that most of them occur predominantly during local daytime. Now, of course, we can make some kind of preliminary summary results here that forward TIDs, these kind of TIDs which originate from the geomagnetic equator, are not as frequently observed as equatorial TIDs, as we know during storm conditions. And these kind of gravity waves that may result into forward TIDs that originate from the geomagnetic equator are very difficult to track. And the main reason is that their amplitudes are too low compared to those that come from auroral regions or high latitudes, And that point was seen long time ago in 1969. So it's not really new. And because of that, the authors in 1969 concluded that for you to be able to see them, you need a dense network of observations. And that is what the GNSS receivers are doing for us here. And we've seen that our analysis show that the forward TIDs are largely constrained within 10 to 30 degrees around the geomagnetic equator. So they don't really propagate far as one would see the cases which are coming from the high latitudes. Now, so the question would be, why is it that these kind of TIDs are not detectable far away from their source, for example, in mid-latitudes? And we think the answer may partly lie in the orientation of the physical mechanism that is at play, that is driving the ion-neutral collisions at the equatorial and auroral regions. And that's what I'll be explaining in the coming slides. So we think that the changes in electrodynamics could have a role, and specifically we've quantified these changes based on the equatorial electrojet observations during geomagnetic storms. Okay, so why are these kind of TIDs different from auroral regions and from equatorial regions? We can start from auroral regions. We know that the gravity waves within high latitudes are generated through direct heating of the atmosphere. That's what's called geoheating or particle-to-particle heating. We know that Lorentz coupling plays a very important role in generating these kind of TIDs. And while we are talking about Lorentz coupling, one must be mindful of the orientation of the magnetic field in high latitudes. So if you look at the current density, the cross product of the current density and the magnetic field, we know that because of the orientation of the magnetic field, which is almost vertical, the Lorentz coupling transfers momentum directly horizontal to neutral gas. And so from the onset, we know that Lorentz coupling will be more effective in generating these gravity waves in high latitudes compared to the equatorial latitudes. And of course, we know the other mechanism is called particle precipitation. You come to equatorial regions, we have Joule coupling as well, and we have Lorentz forcing. But because of the orientation of the magnetic field, the magnetic field itself is the geomagnetic field lines are almost horizontal over the equator, and therefore the Lorentz force is vertical. Now, there are some other mechanisms. So the difference really, the reason why we think the waves which are coming from high latitudes can propagate all the way to the other hemisphere, while the ones which originate from the equatorial regions are confined to about 30 degrees latitude from their source origin, is because of this kind of Lorentz coupling. That's what we think. Okay, so for us to try and link electrodynamics to these kind of observations, we are using the differential magnetometer approach. And this is a very well-established method. What you need is that you need a pair of magnetometers, one at the equator and one just off the equator by about 6 to 9 degrees. And as we know, the one which is at the equator is going to respond to a number of current systems, including the equatorial electrojet. While the other one, which is off the equator by 6 to 9 degrees, is going to respond in approximately an identical way to the one at the equator, but is going to have an absence of the contribution of equatorial electrojet. And the reason is because the equatorial electrojet is just a strip of current which is flowing within plus or minus 3 degrees. And therefore, if you do a direct subtraction of the H at the equator, the horizontal component at the equator, minus the horizontal component of the equator, so the equation here has a mistake, a typo, of the equator, what you remain with is the contribution of the equatorial electrojet. And we know that that contribution itself is directly proportional to the vertical E cross B drift. And that has been shown experimentally in the paper by Anderson in 2004. So what Anderson did was to plot for a number of days, which are shown on your right-hand side, was to plot the changes in delta H, which is now the EEJ, the equatorial retroject, and plot it alongside E cross B from the Julia measurements over Kikamaka, and you can see the fit. And therefore, in absence of actual E cross B drift, one can use delta H as a proxy to tell us how the aerodynamics are behaving in low latitudes. Okay, so let's look at the test case. I'm showing the case of changes in the delta TEC as a function of time and latitude over the American sector. And this we've looked at the 60 degrees south to 30 degrees north latitude. And the longitude sector is covering 30 degrees, 40 degrees west, 70 degrees west. And what is plotted here is delta TEC. So the changes in TEC when you do the differences between the fitted and actual TEC, and that's what the color bar shows. And where you see the more blue values, those are depletions, and where you see the more red values, those are enhancements in TEC, in delta TEC. Now, the important part that is linking electrodynamics to what we are observing in low latitudes is the bottom panel. The bottom panel, and I think I'll spend some time on this. So this is time in UT on your x-axis, and what is plotted in blue is the E cross B from Julia measurements. So that one normally operates during local daytime. And then we have the delta H that has been estimated over the same location. So we are using delta H over Kikamaka. Now, if you try and look at what is happening, so in this line, the vertical red line, the solid line, is where we think there could be some kind of waves which are coming from the geomagnetic equator. I hope you can see the cursor where I'm pointing. And if you relate that one to the changes in delta H, at the same time changes in E cross B, you'll see that you have an enhancement, and at the approximately same time when you have an enhancement, you have these kind of waves being launched from the geomagnetic equator. So that's one typical case, but we can have another typical case too, between 12 and 14, I think it's around 14 UT. You can see the same case around here, and in this case, you are seeing it as changes in delta H. But we have the third case just after 18 UT. Once again, we have these kind of lines which seem to be directly proportional. And therefore, we think that what is happening within the aerodynamics is contributing towards launching of this kind of gravity waves from the geomagnetic equator. So with that, let's look at the other cases. And these are busy graphs, and so I'll choose one to focus on, but the explanation is almost the same for all of them. So let us look at the one on your left-hand side, no, right-hand side, 40 degrees south, 60 degrees north, longitude 50 to 70 degrees west. That is the American sector. So let's focus on that. The red dotted line is the approximate of the geomagnetic equator. This is what I had already explained before. These are the fits, and this is another fit. And once again, you'll see that one is sort of the mirror of the other one. So the top panels that were talked about. What we had not talked about are the bottom panels, so the middle one and the last one. And let me focus first on the middle one. Either of them, whether it is or they are all B, but we'll look at one of them. So let's look at the one on your right-hand side. So this says delta H in blue for the 2nd of March 2017 and monthly median delta H for March 2017. Now, if we are saying that the changes in aerodynamics or in delta H could have an influence in these kind of waves which we are seeing in low latitudes, one of the important things that one needs to think about is how do you know that a particular change is going to trigger the atmospheric gravity waves launching? For that, we need the approximate background variability of this kind of electrodynamics. Now, the background variability that we've done now is we've chosen to use the monthly median delta H values. So if we have a case where we are observing this kind of observations, for example, on your right-hand side in A, then we go and look within that month, we look for monthly median delta H. Once we've got the monthly median, and by the way, the reason why we are going for monthly median is because it's less sensitive to outliers. And once we do that, then for us to have these kind of changes in delta H leading to launching of draft waves, then the values of delta H must be greater than the corresponding monthly median. And that is what we are showing in the black lines here between just before 18, I think between 17 and 18. And if you blow up that one, you magnify that, then you see this inset here. So delta H as a function of time, then magnify the ones which are in the vertical lines, you get this kind of figure. And at this approximate time, when you have the maximum value of delta H, this time is linked to what is happening in the delta H figure. So now we take the approximate time of the launching of the draft waves, which we get from here, from this fit. Then we take the time corresponding to the maximum delta H, which is indicated by these black dots. And then we plot that one statistically. And that is this one, the last panel, which is a scatter plot of estimated launch time of TIDs vis-a-vis the time of maximum delta H. And for this, we are seeing the black dots and the red crosses. The reason is simple, is that we used, because of lack of data, we used different magnetometer pairs. But irrespective of what you do, you'll see that the correlation is almost close to 1. And therefore, that tells you that the estimated launch time of TIDs and the time of maximum delta H have a 1-to-1 correlation. So this is over the American sector, and on your left-hand side, it's exactly the same procedure, but over the African sector. And you'll see the correlation is almost in the same range. Now, so we know before that numerically it had been suggested and shown that the changes in EEJ can have influence in contributing to atmospheric draft waves during disturbed conditions. And the main physical mechanism that is causing this is really Lorentz coupling of ions to neutrals through collisions. And so it's essentially Lorentz coupling that is the main mechanism for driving these kind of draft waves from the low latitudes. And so you can quantify that through electrodynamics. Okay, now, so there are some important points to note. For those who are interested, you can always go to this other paper. But there are some questions which we've not been able to address. So one of them is that, so the first one is during storm conditions, this kind of forward TIDs from the equatorial region are largely observed during local daytime. And I think the reason is really the underlying mechanism is that the changes in EEJ, we know EEJ itself is actually a local daytime phenomenon. And so the changes in EEJ can only trigger atmospheric draft waves during local daytime. So I think that has got to do with the natural changes within the equatorial regions. But the outstanding question that we have not been able to address is why are there more polar TIDs in the African region compared to the American sector? That we've not been able to address. The other one is why do we have more polar TIDs during recovery phase than the main phase? At least we've seen this one in a clear way statistically over the African sector. That we've also not been able to address in this talk. And for those who would like to know more about this kind of topic, please you can contact me on this email address. And with that, thank you very much for your attention.
Yeah, thank you, John, for a very clear and precise talk. And I think that you have almost everything. I mean, actually 100% everything. It's also rarely that usually we ask the speakers questions. It turns out now the speaker asks us questions, and that's why I ask the audience whether anyone could answer his question, answer John's question. And I have another expert, actually listening to your talk. The one I recognize, I know the names. I would just ask them, invite them to to answer you. Maybe I could ask first Professor Yokoyama. Was it Yokoyama? Are you there?
Oh yes, I'm here. Yeah, it's difficult. Yeah, as you know, that equatorial plasma bubbles are also occurring more in the African longitude. Then we don't have clear explanations. So maybe the similar mechanism for TIDs or plasma bubbles, something special in the African longitude.
But do people know why?
No, we don't know.
So you just say that maybe the same thing, right? Yeah.
Yes,
right.
Right.
So you could then have one stone for two birds. Yes. And I can see you have questions to him. Your own question.
No, thank you.
Okay, thank you, Professor Yokoyama. Andres, are you there? Andres is now in Madrid. I think he's in Madrid. If he's around, and I'll ask him come back. And then Professor Haixia Liu.
Yeah, I'm here.
Yes. Oh, you have questions to John?
Yeah, I do have a question about the fitting. The VTEC changes are derived from the difference between the VTEC and the fitting VTEC, right? I wonder if these VTEC changes contain some signal or features caused by the irregularity.
Okay, so you are asking whether the fitting, if for example, in this case we are using a fourth order polynomial. So you are saying if, for example, we change the order of the polynomial, could it change the features or results? Is that your question?
No. My question is, because the fitting makes the curve, the VTEC, the curve quite smooth, right?
Yes.
But the LOS might experience some irregularities, the depletion, or something like the professor said, the plasma bubble. Yeah.
Okay. I understand your question. So in this kind of fitting we are doing, we are actually fitting at different latitudes and longitudes. We are not doing over a particular station the way people usually do on the vertical TC. No, we are not doing that. We are doing it as a function of latitude and longitude where the observation exists.
Oh, I see. I understand. Okay.
Yes.
Yeah.
And so I do not think that the features would really change even if we change that.
Yeah. Regarding your questions, too difficult. Yeah, for me.
I think we do have. If you look at the first question which I have, even when you look at the occurrence of ionospheric irregularities, there are more ionospheric irregularities over the African sector compared to the American sector. And I think what is very difficult to understand is that usually when you look at ionospheric irregularities, people used to think that the main driving mechanism could be the magnitude of Lorentz force. But actually, the Lorentz force, the E-cross-B drift, is greater in the American sector than in the African sector. And therefore, you'd expect more irregularities in the American sector than the African sector. But it is the reverse. And so no one knows why.
Okay, thank you.
All right, thanks.
Okay, thank you. So if you have questions, please raise your hand, or, and I could recognize you, or you just ask the questions. And I think that I can see Sukriya. Are you there, Sukriya? Sukriya, she's from Malaysia, and she was the speaker last time. And I thought that she might want to have to ask you questions. If not, I can see also a Dr. Daya Sankar. Daya Sankar, are you there?
Yeah, I am here.
Yeah, your questions?
Yeah.
You're doing a seismology, right? Earthquake.
Yes. First of all, can this tide be used for the precursor of earthquakes occurrence? Because it has been seen that before the earthquakes, there is some ionospheric disturbance. Concern of the ionospheric ions are increased during the preparation of the earthquakes, just before the earthquake.
Okay, so if I understand your question very well, is can this kind of method be used to understand the precursors to earthquakes? Is that the question?
Yes, yeah.
Okay. So let me first say that I am less qualified to say that, but I am aware that there is a very active group from Russia, and I think, I don't remember the other groups, but they are looking at ionospheric changes as precursors to earthquakes. And in fact, they do this kind of data trending to show changes in TEC. So the methodology, they are using almost the same methodology, but I'm less qualified to say whether that one really causes earthquakes. And so I want to be able to answer that. But yes, people are using similar methodologies to try and do that.
Okay, thank you.
So John, do you know the
Okay.
people there? Do you know the people there?
I can look for the contacts and send you. Yes, they are very active.
Yeah,
the Russian guys doing that.
Yeah, we do have also a group here actually right here in my building, was also doing atmospheric trying to look for signature produced by earthquake in the ionosphere.
Okay, I'm going to send you the contacts. I think what is clear that when you have an earthquake, you can generate gravity waves which turn into IDs. That is very straightforward. So after the earthquake, it is very clear. But the other groups are looking at these kind of things, the changes in atmospheric TEC as precursors. So before the earthquake occurs. But after the earthquake, it is straightforward. Before the earthquake, that one I'm not sure, and I can give you the contacts of people who are doing that one.
Yes, after the earthquake, yes. I mean, the whole earth shakes a little bit. Okay, I can see that there's a message saying that Professor Ovando, can you have raised your hand? Can you want to ask a question?
Okay, thank you so much. Thank you, John, for such a wonderful talk. So, John, just a follow-up on one of the questions that earlier on came up. I think that was a very important question where one of the participants asked what you will comment on the frequency of irregularity occurrence and this occurrence of poleward TIDs, particularly outside the geomagnetic storm conditions. I think I'm also interested to get your comments on this, and maybe also just to get your comment if you have studied them under nominal conditions, because the low latitude under nominal conditions probably gets more unique than under geomagnetic storm. So have you also looked at them under nominal conditions?
Okay, so you are asking about the occurrence of these kind of waves also during quiet conditions.
Yes, just when there are no storms,
Okay, very good. So we've done that as well, but we've not yet published these results because we are still trying to look for what could be the driving mechanism. But during quiet conditions, they also do exist, but on very small scale compared to storm conditions. But there are some isolated cases, and we have some cases, yes. If you are interested, I could send you one case and you look at, and you'll see they are also there. But not as frequent as during geomagnetic storms. And for those during quiet conditions, we actually do not know what is driving it.
Okay, thank you.
Thank you, John. Thank you.
Yes.
All right, thanks.
I want to say also that I will keep this, we are about to end this session, and thank you so much for coming. And we will keep this open for 5 minutes, so that for those of you who want to receive information or announcement from this series of online seminars on low latitude ionospheric research, please write down your email address to us. Then we will we will send the information to you. So you could do it now for the next 5 minutes. And thank you for if you're interested in that. In the meantime, John, I thank you so much for a very nice talk. And I see you in 2 days. I think see you in 2 days on another platform. Yes.
Yes.
And have a good day. Yeah.
All right.
Thank you.
Thank you once again. Thanks to the participants for coming, and thanks for the invitation.
Right. Thank you.
All right.